Good afternoon to all my YouTube viewers. Myself J Das. In this video, I like to discuss about photoelectric effect. Mainly, we will concentrate on theoretical part of photoelectric effect. Then we will talk about few questions and few problems. The purpose of this video is to boost students' position as they have to come across board exams as well as many other competitive exams. The important point is, in our learning process, we have to know de-learning also very important. Why de-learning is so important? If we cannot de-learn those things, those mindsets who have occupied our memory bank, it may be contaminated information, it may be a sick mentality which is not allowing you to grow because of the circle you are having, the information channels you are having, or the way you take inputs in your mind or in your academic memory bank. It may be that something has to rethink, something has to modify. That is why you know that in any computer or in mobile or any software, a updated or revised version always provides to rectify the software if anything wrong in the system or any any wrong information provided in the system or contaminated due to some reason. Same thing happens in our life. If our mindset cannot change, we cannot take big task, big target. So, it is also that de-learning will help our progress. You de-learn and relearn very fast, your new memory set will give you the direction, actual direction of your life. A small change in your decision may give a very big change in your lives and future. Let us start the subject. When an electromagnetic radiations of suitable wavelength are incident on a magnetic surface, on a metallic surface, then electrons are emitted. This phenomenon is called photoelectric effect. Now come to what is photoelectrons. Emitted electrons due to photoelectric effect is called photoelectrons. Similarly, photoelectric current, the current so obtained during PEE, photoelectric effect, is known as photoelectric current. Now, the point 4. Alkali metals like lithium, sodium, potassium, cesium, etc. gives photoelectric current with visible lights, and metals like zinc, cadmium, magnesium, etc. gives photoelectric current with ultraviolet lights. Number 5, photoelectric current is directly proportional to intensity of light. Through experiment, this can be confirmed. Now, photoelectric current and intensity of light plot will give a straight line. Now, this is a very simple experiment. There is a slit through which monochromatic light can be taken, and opening of the slit will decide how much intensity you are allowing in the system. First you keep 20% opening, then 50%, then 80%, then 100%. So many data will generate and it will give a straight line like this. Now, graph between photoelectric current and anode potential difference. It will give a unique curve like this, that when you will keep that is a vacuum tube, is this experiment done within a vacuum tube. One side is cathode, another side is anode. When photons are allowed to fall on the metal which is being placed on the cathode, there will be a electron generation if it is a photosensitive material. Now, if we keep the anode potential 0, we will see there is a current. If anode potentials further increases from small value to large value, it will be observe a characteristics plot that it will go up, current will go up, then it will become flattened. That means whatever electrons are generating from that, it is being exhausted when it will speed up initially and then it will be exhausted and saturation will take place. So, current will be flattened. Now, if we go for negative potential, then what you will see that gradually current will decrease and when potential, suitable potential will be given, negative potential will be given to anode, then electrons are not invited anymore. So, they will stop giving currents, they will not come, even the highest kinetic energy level electron cannot come. So, this will call as a stopping potential. The stopping potential it is the minimum negative potential with respect to anode to stop photoelectric current to 0 level. Now, come to point number 7, Einstein's photoelectric equation, very important, that is Hf equal to W naught plus kinetic energy. Kinetic energy automatically Hf minus W naught. W naught is called work function. It means for any metal, photosensitive metal or a less short photosensitive metal, what we are going to select, it has its own work function value. After taking this much energy by that substance, then remaining energy will be released as a kinetic energy of electron. So, Hf is the total energy what has come from photon minus work function. Then the excess energy will be converted to kinetic energy, and this kinetic energy can be replaced by EV naught, that is equal to Hf minus F naught. Here F naught means frequency which is we are getting from source from photons minus F naught. F naught is called threshold frequency. This particular frequency for a particular material, what it means, below this frequency, if incident light has below this frequency, it cannot emit any electron. So, this is called threshold frequency. If a plot drawn on the basis of that V naught versus F, we can see that there will be some particular frequency below that that metal is not responding as a photosensitive material. So, that is threshold frequency. Now, in the other plot we can see there are two A and B is given. Here it means two different type of metals has been taken. For A it is F naught, is the F naught 1 is the threshold frequency. For the second metal it is F naught 2 is the threshold frequency. Now, by extrapolating to negative side of potential, you will see, we can see that W 01 by E and W 0, that means work function divided by electron, that will meet at that point, that value will be available from here. Now, next point number 9. If intensity of the light increases, keeping frequency constant for the incident light, we will get this type of plot. The plot which has been shown here, you see that I2 has a higher intensity, so it will be higher in current, but against at saturation zone it will be flattened. But intensity can give current magnitude slightly higher, keeping particular positive potential of the anode. But the most important point that V naught stopping potential will be fixed for a particular metal. Whatever intensity comes, higher the intensity, but the stopping potential will remain same. Now come to point number 10, keeping intensity same. If we take different frequency of incident light, then we can see stopping potential will vary. Higher the frequency, it will have a higher stopping potential. That is why you can see that as intensity is same, it will have same saturation type of current, but in the as frequency is incident light is higher, so it will have a higher stopping potential. That is the information available from here. Next point is 11, laws of photoelectric effect. Number 1, A. The number of photoelectrons emitted per second is proportional to the intensity of the incident light. From the first plot, number 5, we can see this is there. This information is there, directly proportional with the intensity of light. Now come to B. Below threshold frequency, no emission of electrons takes place, whatever intensity may be given. That already been discussed. Each metal has its own threshold frequency, below that it won't respond as a photoelectric material. Now the next point is C. The maximum value of kinetic energy of electron solely depends on the frequency of the incident light, not on the intensity. Number D. The emission of photoelectron is an instantaneous process. It is not that it will absorb certain amount of energy and then it will start emission. It is not that. It starts instantaneously. It is less than below 10 to the power minus 9 seconds. So response is simultaneously. Failure of wave theory to explain photoelectric effect. These failure points are coming in the exam, and especially in the board exams. Now, we can see point number 12A. There are at least 3 failures are there, we must discuss. Intensity problem. What is that? If intensity of light falling on metal is increased according to WTL, oscillating electron field vector E of the light wave increases in amplitude. It shows from experiment that is kinetic energy is not depends on intensity of light. Kinetic energy is not depends on the intensity of light, it depends mainly on the wave theory of light. WTL means wave theory of light. I think this point is understood. Next point B, frequency below frequency problem. According to wave theory of light, photoelectric effect should occur for any frequency of light. According to wave theory of light, photoelectric effect should have started for any frequency, but in actual this is not happening. But found that photoelectric effect starts above minimum frequency known as threshold frequency. Already all these points are discussed. This is a failure, wave theory and particle theory, quantum theory. Now come to point number C. According to wave theory of light, electrons will take some time to accumulate enough energy to escape from the metal surface, but from experiment found at suitable frequency, electrons eject instantaneously. So, wave theory of light fails to explain photoelectric effect. Now come to questions and problems. Now, first question, intensity and frequency of incident rays both are doubled. What is the effect on stopping potential and saturation current? Answer, frequency is double, so energy of the incident light will increase, almost double. So, work function of the metal remains same. So, kinetic energy will increase and stopping potential will also increase, because kinetic energy and stopping potential relations are known, that is half m v square, velocity of the electron, equal to E v naught, E v suffix naught, that is stopping potential. So, doubling intensity current will increase, but stopping potential has no effect. Now, come to question number 2. The maximum kinetic energy of photoelectrons from a metal surface is K when incident light wavelength is lambda. When wavelength increases to lambda by 2, what happens to kinetic energy of the photoelectrons? There are 4 choices. Let us work out for this. As work function remains same, because work function is not changing, metal is remains same. So, kinetic energy max equal to total energy minus work function, that is hc by lambda minus work function. Now, when lambda changes to lambda by 2, then kinetic energy dash max will be hc by lambda by 2 minus w. So, it will give you twice hc by lambda minus w, or substituting hc by lambda from the we can dump here 2 hc by lambda minus w and outside the bracket plus w, so that it will balance this position. Now, kinetic energy dash max will be twice the twice the energy max which is available from the previous equation. Kinetic energy max, kinetic energy max. Now, we can see kinetic energy dash max will be 2 times kinetic energy max plus work function. That means kinetic energy dash max will be greater than 2 times kinetic energy max. This is available in answer number B. So, B will be the answer. Next question, question number 3. The photoelectric work function of potassium is 2.3 electron volt. Lambda is given 2800 angstrom. Find kinetic energy in electron volt and stopping potential. Now, from here we know that E equal to 12375 divided by lambda in terms of angstrom, that will give the amount of total energy. Actually Hc by lambda in terms of angstrom, this is the expression. 12375 over 2800, it will give us 4.4 electron volt. So, kinetic energy maximum will be 4.4 minus 2.3, which is work function, equal to, it will give us 2.1 electron volt. So, stopping potential will be 2.1 electron volt. Now, come to question number 4. If the work function of 3 photosensitive materials are 1 electron volt, 2 electron volt and 3 electron volts respectively, then the ratio of the respective frequencies of light that produce photoelectrons of maximum kinetic energy 1 electron volt from each of them is, there are 4 choices. I mean here kinetic energy remains 1 electron volt. The expression is known to us E V naught equal to H nu minus W suffix naught, that is work function. Maximum kinetic energy for all material is 1 electron volt. Now, then total energy E1 will be 1 electron volt plus work function, that is 1 electron volt, that means 2 electron volt for first metal. Similarly, E2 that will be for second metal, that is 1 plus 2 electron volt, that is 3 electron volt for second metal. Similarly, E3 will be known, that will be 4 electron volt for third metal. Taking ratios lambda 1, lambda 2 and lambda 3, we can get E1 by H is to E2 by H is to E3 by H. So, 2:3:4 will be the answer. Choice number B will be the answer. Next, come to question number 5. The stopping potential for a metallic surface illuminated by monochromatic light of wavelength lambda is 4 V naught, while the another light of wavelength 3 lambda, it is V naught. The threshold wavelength of the surface for photoelectric emission is, we have to find out wavelength for the threshold wavelength for the metal. Now, there are 4 choices. According to the question, it is understood that E into stopping potential, that is V4 V naught equal to Hc by lambda minus Hc by lambda naught. In the second equation, E V naught, that is equal to Hc by 3 lambda, because wavelength, now incident light wavelength is 3 lambda, minus Hc by lambda naught. We have to find out lambda naught from here. Dividing 1 and by 2, then we can get 4 by 1 equal to Hc within bracket 1 by lambda minus 1 by lambda naught, bracket close, then again divided by Hc within bracket 1 by 3 lambda minus 1 by lambda naught. Solving this to this one, we can get lambda naught equal to 9 lambda. That means choice C is the answer. Now, come to next question, that is question number 6. When light of wavelength lambda is incident on photosensitive surface, the stopping potential is V. When light of wavelength 3 lambda is incident on same surface, the stopping potential is V by 6. The threshold wavelength is There are 4 choices. It is similar to previous problem, that is E V equal to H C over lambda minus H C by lambda naught, and E V by 6 equal to H C by 3 lambda minus H C by lambda naught. Solving this, we can get lambda naught equal to 5 lambda, and easy problems we can understand. Next question, question number 7. The work function of a substance is 4 electron volt. The longest wavelength of light that can cause photoelectrons emission from this substance is approximately, there are 4 choices, we have to see for it. We know the work function equal to W equal to phi naught, these are the symbols used, that is equal to H C over lambda naught. We have to find out lambda naught, H C by phi naught, lambda naught equal to H C by phi naught. So, 1240 electron volt nanometer, this is a standard value, divided by 4 electron volt, that will give us 310 nanometer. The answer is C. Now, thank you very much. You can use this for your first phase development. In the next video, we will give competitive exam standard problems on photoelectric effect. Share this, also like it, and subscribe, so that continuously you will be getting our support. Thank you very much.